let's draw a picture or two here. And so a fair amount of this lesson is going to be drawing the diagram here. So make sure you get your piece of paper. Whatever I write, you got to copy. Now, if you didn't draw a picture of Roy G. Biv, whatever, I don't care. This part you got to draw. Okay, here we go. All right, so on your paper, now this isn't the easiest thing in the world to draw. I want you to do your best. I know you can do it, but just be careful, okay? It takes a little skill. What I'm draw is a wave here. Oops, I don't want the paper to move. And what you got here is a nice long wavelength. And so the wavelength would be from, it's called peak to peak or trough to trough. I'm not going to get bogged down in too many terminologies here, but I want you to know that one, wavelength, okay? Okay? And so if you hear the term frequency or wavelength, it's talking about the same thing as that structure of the wave. And there's other terms like the height of the wave is how much energy the thing has. It's the amplitude. But again, I'm not going to bog down in too many technical details except for the wave length. That's the one you got to know. So here you got a longer wavelength. Okay? And here you could have one. It's the same thing. It's just a wave of electromagnetic radiation, electromagnetic wave, but it's got like a medium wavelength, like the baby bear wavelength. By the way, there's a symbol for this that they use. It's a lambda. Okay, so that Greek letter also is another way of saying that stands for wavelength in the formulas. And you'll get to the formulas and stuff when you're in college or something. But so we're not going to worry about it. Or you can have the shorter wavelengths. It's the same stuff. It's the same thing going through space at 186,000 miles per second, 300,000 kilometers per second. And there's wavelength again with the lambda. So I want you to know the wavelength here. Here you got a shorter wavelength. And here you have a longer. Now, could you have longer than that? Yeah, of course. You can have it stretched out as long as you want. You can have a wave where it's just one wave from here to the moon. Sure, why not? Or you can have a shorter wavelength. It's so short it's like smaller than an atom. Yes, you can have that. In fact, those do exist. All right. So we got the electromagnetic waves and the difference longer and shorter. Okay. Now you should have that drawn. And if you don't, stop the video and you pause it and then go on. All right. So now you know light is electromagnetic waves and that they have different lengths. That is a key thing to understand these theories that they've arrived at, discoveries of the structure of the universe that we're going to get into the next lesson we have. But this will be kind of prerequisite to understand that next lesson. So there we go. All right, so you got the waves. Now, let's move on to what we have here again is the wavelength. Velocity is c. Remember the speed of light is c equals mc squared. We did that. And so for measuring the frequency, which is that Greek letter lambda, frequency, they use V and whatever. Okay, so we got the peak and the trough, blah, blah, blah. Now, here's the deal. The difference between red and blue. So you think, oh, your eyes receive various, light, and we experience the color blue in our brain, or they experience the color red in our brain. Well, the difference between red light and blue light is the wavelength. That is the difference. It's the same exact stuff. It's the wave of the electromagnetic force, except red has a longer wavelength, blue has a shorter wavelength. That's the difference. And by the way, that right there is one of the key ideas to understand when we get into the next lesson. So I want you to make sure you got that, okay? So red, the difference between red and blue is that red has a longer wavelength, okay? So it's the same thing. It's electromagnetic waves, but just it has a different length of wave. Okay, so write that down. If you need more time, pause it and move up. Red and blue. So which one's longer? Say it. Red, right. Which one's shorter? Say it. Right. Okay, so blue is shorter. So what you have then is the whole spectrum where it's like red is the longest of the visible spectrum and violet is the shortest. And the difference between red, orange, yellow, green, blue, indigo, and violet is the length of the wave. Okay? And so it's progressively longer as you get toward the red, progressively shorter as you get toward the blue or the violet. Okay? A lot of times they'll talk about the blue end, but it's, violet, of course, is visible light in the shortest of the wavelengths that we see. And yes, it's possible for light to be longer than red, so long as we can't see it. Okay? And we'll get to that, in fact, coming up right next. So, there are many kinds of light that we cannot see, and depending on the size, again, some of these wavelengths, this is like the size of a nucleus of an atom, whereas these are like the size of the Empire State Building and stuff, which can be literally limitless. And then you have the visible spectrum,